Hi everyone, today we are going to solve one of the popular problem in BST, which is k smallest value in BST. So basically this problem is pretty much easy for the people who understand truly about BST and its property, all those things. If you know the property and deep understanding about BST, you can just solve this problem within matter of seconds. It's pretty much easy. But in this video, where we're going to explore what is the a naive approach, a brute force approach, and then we are going to solve optimal way. And without wasting much time, let's get started. So first, let's talk about the problem statement. So basically, you will be given a binary search tree and number k. So what you have to do is that you have to return the kth smallest number from a given BST, which means if you look at this particular tree, if I write this number in a sorted order, this will look like this: 2 and then 3 and then 4, 5, 7, 8. So this is the sorted order, guys, for this particular tree. And which is the third smallest element? Tell me, which is the third smallest element? 4. So you just need to return the kth smallest element. If n is going to be 2, then which number you will return? The second smallest number from a tree. Which is the second smallest number in a tree? Tell me, guys. This is 3. You have to return this value. I hope the problem statement is very simple and very straightforward. Now let's talk about the naive solution or a brute force one. So what everybody will think in their mind is that we can just traverse this array. The first step is going to be traversing. What is the next step? So while traversing this tree or while searching this tree, we need to store the number in some particular place or some particular container. So it can be an array. We can store all the number in an array. For example, we're just traversing it, right? We'll go 5, we'll store this 5 in an array. We're going to store this 3 in an array, 2, 4, 5, all these things. While traversing the number or a node, we're going to store that particular value in some kind of container. So the container is going to be array. So let me write down that particular step as well. Store in a container. So it's going to be an array, right? As we discussed, it's going to be an array container. And then what's the next step? Tell me, guys. Once you have all the element, what should be the next step? So how you can find the k smallest element? By sorting it, right? So next step is going to be sort the array. So once you sort it, you can simply identify the kth smallest element. So just return the smallest element. Pretty simple. This is the entire algorithm for a brute force solution. Now, if you talk about the time and space complexity, it's going to be pretty huge. For traversing, tell me, guys, for traversing an entire tree, what is the time complexity? It's going to be big O of n, because you are just visiting every node only one particular time. So for traversing, it's going to take big O of n time. Am I right? And then if you talk about space complexity, for storing an array, what is the time complexity? For n numbers, you need n space. So space complexity is also going to be big O of n. And to sort an array, what is the time complexity, guys? Tell me. It's going to be again time complexity of big O of n log n of time to sort an array. And for simply returning it, it's going to be time complexity of big O of 1. Now, if you just add up the time complexity, the overall time complexity is going to be big O of n plus big O of n log n, and again big O of 1. You can just simply neglect this, but the overall time complexity is going to be big O of n plus n log n, which is pretty huge. In terms of optimized solution. In optimized solution, we can do much more better. And you know the property of BST, right, guys? So BST property states that all the node on its left is going to be less than the node, I mean the root node, and all the value to the rights are going to be greater than. So we can utilize this property with in-order traversal. So what will happen if you do in-order traversal in BST is that you're going to end up getting the number in sorted manner. That is super good, right? That is with the property. If we just simply apply in-order traversal algorithm, we are going to get the numbers in a sorted manner. The the way how we are going to do is that left node and then the root node and then right. This is the order in we will visit the node for in-order traversal. And if I write down the in-order traversal of this particular tree, to look like this. We are going to get 2, we'll get a 3, and then 4, then 5, and then 7, and then 8. The order will look like this, guys. And one more thing, guys, if you don't know about how does in-order works, please learn it by yourself. If I explain it, the video will get keep on increasing. So I'm not going to explain in depth about in-order traversal. We are just going to utilize the in-order traversal algorithm only, not explanation of it. So now let's continue the our algorithm. So what I said is that we are going to utilize the in-order traversal. And while traversing the BST, we're going to end up getting the numbers in sorted manner, right? We can utilize this and we can stop the traversal when we visit kth node. I mean, we are going to have the counter. We are going to have the counter. So whenever we are just visiting a node, I mean, whenever we visited a node, we are going to increment the counter. By this way, when we reaching the counter value to the k, we can simply cut off this loop and we can simply return the value, guys. This is pretty simple solution. Now let's see the dry run of it. Now let's try the pseudocode for this, guys. It's pretty simple. So the in order traversal. So I'm going to write a function in order, and we are going to receive the node, the current node, which is going to be the root, and that's it. And outside of this, let me declare an variable. Okay, we're going to have the main function, and then inside the main function we're going to have the counter initially we're going to set to the 0, and what we are going to do is that we are going to write the in order traversal algorithm. Let me write down it very quickly. So if there is no root, we are going to simply return, and then I'm going to go to the left side, right? Left, root, right. So we are going to call the recursive in order of root dot left. So what is the next step, guys? Once I visit the left node, next I have to reach the current node, right? For now, let me print current node. Okay, which is root dot value. I'm just going to print the value. That's it. Next step. Now node is done. Next step is going to be right value. So in order of root dot right. That's it. This is the entire code for the in order traversal. Let me erase this off. So this is the entire code for in order traversal, guys. Outside of this particular function, we're just going to simply call in order of root node. That's it. Pretty simple. Now this is the typical pseudocode for in order. Now we can simply modify this. Where we have to modify, that is like pretty tricky in this particular problem. So we are going to modify in this particular place. In this particular place, we are going to modify. Okay, how this modify will look like is we are going to increment the counter over here. So count plus plus, and we are going to check the if condition. If counter is equal to k. I just forgot, right? So in this function, I have to get root node as well as the k value. Now I'm going to check if count is equal to k. If it does, I can simply return root dot var. So it's pretty easy and a little tricky for understanding this particular case, because when we will tell visitor is that in this particular step only, if you look at this thing, this will look for all the right value, and the next step is we have to see the current node, which is visiting state of the current node. So we are going to consider that as an visited state. If I just show you guys that a small dry run, let's take this particular tree. Now I'm going to start the in order with 5. Am I right? So in order with 5. Am I right? Now I'll just keep on coming to this particular code. I'm going to check this condition. No, it's not passed. Again, I will send the right side of it. Okay, now I'm going to send the right side of it. So for short down, I'm going to short very in order of 3. Am I right? Now again, this recursion function goes back. I'm going to check this condition. Again, it will send to the right node. So the flow will go like this. 2. Now again, this in order will go like this, and it's going to check this particular node, and this particular step, it will send the null node because there is no node for this particular step, right? So it will just send the null node, and when I reach this particular step, I mean again the recursion function calls, right? This condition passes. So if there is no node, simply return. So it's going to simply return back, right? It's going to simply return back. And now what is the next step? So we just visited right step, sorry, left side. Now next I just want to increment the counter. So initially the counter is going to be 0. Now we just increment the counter to 1. Am I right? It's pretty simple. Now I'm going to check whether it's equal to k or not. Right now our k is 3. No, it doesn't. So what is the next step is we are going to visit the right child. So do you have any right child for 2? Nope, we don't have. There is null. Again, this will return back to this particular node. Now the traversing for 2 is over. Now we just go back to the 2 and we are going to come to this particular step. If you remember from 3, we just called left side, right? From 3. Now this particular step is done. Now we are going to increment counter from 1 to 2. And we are going to check whether it's equal to k or not. No, it doesn't. So what is the next step, guys? Next step, we have to visit right side for number 3. Let's visit right side for number 3. We do a 4, and again the recursion call goes back and we'll start doing all this check. So for 4, we're going to check 4 is null or not. No, 4 is not null. Again, I'm going to check for the left side, and then right side, all those things. So if you look, 4 is going to be leaf node. So obviously we are going to have null only. So once I visited the left side, I'm going to visit the node 4 itself, right? If you remember, once I'm done with the left, I'm going to increment the counter. So I'll increment the counter to 3, and then I'm going to check whether if count is equal to k or not. Right now it does. Count is 3 and k is also 3. So I can simply return the current node, which is 4. The answer is, the problem is pretty simple, right? Right now we don't need to visit the entire element. We are just going to visit at most k elements. That's it. At the worst case, it's going to be n. N is nothing but when k is equal to the size of an array. Let's say this, we have how much numbers? 1, 2, 3, 4, 5, 6. What if we have to find this 6th largest number? At the time, the time complexity is going to be big O of n. Obviously, at the worst case, it's going to be big O of n, but the best case is going to be big O of k. We are just going to visit only k particular node. That's it, guys. I hope you understand this particular problem very much. We'll meet again in one more video. Until then, keep watching, keep practicing. Bye.